the next thing we need to be able to do is to be able to analyze the limits as x approaches infinity or negative infinity just by looking at the algebraic representation of the function. Reminder, if it's a polynomial function, all you have to do is look at the highest degree term of the polynomial function and remember what the graph does of that function. For example, this is 3x to the fourth, which is even, so it will have the same in behavior as our memorized x squared graph. So as x approaches infinity, my y values approach infinity, and as x approaches negative infinity, my y values also approach positive infinity. For a rational function, the way to find the limit of a rational function as x approaches infinity or negative infinity is to divide each term in the numerator and the denominator by the highest power of x. So I'm going to rewrite this as 3x over x squared plus 2 over x squared all over x squared over x squared minus 1 over x squared. And then we're going to analyze each of these individual fractions to see what they do as x approaches infinity. A constant over a variable going to infinity or negative infinity, we saw from the graph of our reciprocal function, approaches 0. Constant over a variable approaches 0. This simplifies to 3x over x squared would simplify to just 3 over x, which again is a constant divided by a variable, so that would approach 0. And x squared over x squared simplifies to be the number 1. So this simplifies to be 0 plus 0 over 1 minus 0. And then if I take the limit of a constant, which is constant is 0, as I approach infinity or negative infinity, I am going to approach 0 for both of these. There is a shortcut for rational functions, and that shortcut is just to look at the highest degree term in the numerator and the denominator. The reason why we can do this is I've got this x squared function. Subtracting 1 from something that's going very, very big really is going to be negligible. Same thing, adding 2 to something that's going to go very, very big is going to be negligible. So if I were to simplify this function, it simplifies to 3 over x. And now if I evaluate the limit of a constant over a variable as x approaches infinity or negative infinity, that's our memorized reciprocal graph, which approaches 0, which gives us the same 0 that we got before. So for the next function, we're going to use the shortcut, and you're allowed to use the shortcut on any test, quiz, or homework. The highest power in the numerator or the denominator is x cubed, so I could divide everything by x cubed, but I can also do this just by looking at the highest degree term and then simplifying. X cubed over 2x, that simplifies to x squared over 2. This is a memorized function. It's got the highest power of 2, so as x approaches infinity, this would approach positive infinity. And as x approaches negative infinity, this would also approach positive infinity. One little side note on this is I can actually use the strategy of dividing by the highest power of x even if I have square root functions. So let's look at the highest power of x in the numerator. That's x cubed. The highest power of x in the denominator is the square root of x to the 6th, which is also x cubed. So the way I'm going to look at simplifying this is I'll keep the highest degree term in the numerator. I will keep the highest degree term in the denominator. I will simplify the highest degree term that's in the denominator. The square root of 25 is 5, so I have 10x cubed over 5. Square root of x to the 6th is x to the 3rd. Simplify this. So this is the limit as x approaches infinity of this is the same as the limit as that, which would be the same as the limit as x approached infinity of this simplified. The x cubes would cancel. 10 over 5 is 2. And we know that the limit of a constant is just that constant. So this function would approach 2, and it wouldn't matter if I was approaching negative infinity, the limit of a constant is still the constant. And from your college algebra or algebra 2 classes, you should recognize that, hey, if I'm approaching a constant, these are horizontal asymptotes that the function is approaching. The last one that I'm going to cover is this absolute value of x function, and it's going to take a little more analysis. Okay, this right here is, well, if I put a negative value in for x, let's start with the positive. If I put a positive value in for x, I'm going to get a positive number here. 1 minus a positive number is a negative, but I'm going to end up with a positive number. So if x is positive, I'm doing this case right now, I end up with something that approaches x squared. Now let's see if I put a positive number in here. I get a positive times a positive, which is a positive with the x squared plus x. And again, the highest degree term would be x squared divided by x squared, which simplifies to 1. So the limit as I approach a positive number is 1. And let's look what happens here. If I put a negative number in here, that's still going to turn positive. Okay, and I put a negative number in here, that's still going to turn positive. So again, it's going to be the limit of basically the x squared over x squared, which also is equal to 1. You want to be careful with the absolute values or square roots of something squared underneath the radical to make sure you end up with the right sign.